Hi everyone, welcome. Today we are tackling an interesting physics problem involving a package in an incline and the spring. Here is the scenario. We have 2 kilograms package that starts from the rest on a 53.1 degree incline. The package is positioned 4 meters away from the spring at the bottom of the incline, which has the spring constant of 120 Newton per meter. We are also given both the coefficient of static and the kinetic friction. Our goal is to determine the speed of the package just before it reaches the spring. Let us first outline the knowns and unknowns based on the given information. We will be using the work-energy theorem to solve this problem as it provides us with the most straightforward approach. Let's dive in. Let us first remind ourselves about the work-energy theorem, which can be written as K1 plus U1 plus W other equals K2 plus U2. Where K1 and U1 are the kinetic and potential energy when the package is at the top of the incline, and K2 and U2 are the kinetic and potential energy when the package just reaches the top of the spring. W other is the work done by the non-conservative force. In our case, the work done by the friction is non-conservative. Okay, based on this equation, let us proceed further. At the beginning, the package is at rest, so the initial kinetic energy, K1, is 0. The potential energy, U1, is mgh. Here h is the vertical distance between the top of the spring and the package. Now let us figure out what is the work done by the non-conservative force, which is work done by the frictional force. Notice that the static friction exists when the package is at rest. So, there will be 0 displacement. Thus, static friction does not do any work. When the package is moving, there is kinetic friction. So only kinetic friction does work. Thus, the W other is equal to Fk.s. But as the friction force is opposite of the motion, we need to put the negative sign in front of it. Now let us figure out the other side of the equation. The kinetic energy K2 when it reaches the spring is half mv square. The potential energy U2 will be 0 as we take the top of the spring as the reference, as we have measured the vertical height of the package from this position. Here, we do not know the vertical height, h, but as we know the angle and the distance between the spring and the package, s, we can use the sine function to figure out h in terms of s, which will be equal to s sine theta. The kinetic frictional force is equal to the mu k times the normal force. To figure out the normal force, we need to draw the free body diagram. It will be easy for us to work on the tilted axis. The normal force is pointing in the positive y direction of the tilted axes. The weight of the package will be pointing downwards as shown in the figure. The weight has both x and y components. The x component is mg sine theta in negative x direction and the y component is mg cosine theta in negative y direction. Since the package is not moving in y direction, the normal force must be balanced by the y component of the weight. Thus, Fk will be equal to mg cosine theta. Now we have the equation to play with. In this equation all the quantity are known except the velocity, v. If we play around this equation, the expression for the velocity will be v equals square root 2, g, s times, sine theta mu k cosine theta. And theta. Now we need to plug in the values and calculate it, which gives us the velocity 7.3 meter per second.